My name is Melchior. I'm a consulting engineer with Juniper, and I'll be presenting today about quantum key distribution and a little bit more in general about quantum networking. During the presentation, we'll also have a small demo on how QKD works, and Ashwin will talk you through the demo and show you how we can leverage QKD in IPsec in this case. So in this presentation, we'll start with a small introduction to quantum networking and what is it and what language are we using, so some terminology. Then we'll look at what quantum key distribution actually is, so how we can use quantums or polarized photons to distribute key material. And then we'll pull that together and see how we can use QKD in IPsec and MACsec and other security protocols and algorithms, and we'll go into the demo. So to start with, touching on a few potential fields of interest of where we could use quantum technology in networking. The first is using a chip, a so-called quantum random number generator, which could be integrated into a firewall or router or server. And that basically uses quantum technology to generate entropy. And with that, you can use that to generate key material. Why would you want to use such a chip? Because the randomness is much higher than using random or urandom on Linux, for example. So the rate it can generate randomness is also much higher. The second field is using properties of quantum mechanics to share a key material. That could be keys that are generated from a QRNG, or could be simply keys that are generated on a router or switch, etc. And you want a safe way to communicate those keys to the other side. The third is a field of interest is post-quantum cryptography, or in other words, security protocols and mechanisms that are quantum resistant. Because one of the things we'll see in this presentation as well is that some of the algorithms we're using are not resistant against attacks from quantum computers. And that leads me to the problem statement. MACsec, or AES 256, which is used in, for example, MACsec and other security protocols, on itself is quantum resistant, especially if you, because you're able to simply double the key size if at one point a quantum computer might be so powerful that it could crack the key. However, the issue is, how do you share that key? Right, so you need to have a mechanism to share a key between two parties. And many of the security protocols we're currently using are based on prime numbers. And if the prime number, if you want to factor that, that is really hard, especially if the prime number is very large. That is really hard for a classical computer. But it is especially a task a quantum computer is really good at, especially when using the Shor's algorithm that describes how a quantum computer could factor a prime number. So at one point, it is expected that a quantum computer becomes powerful enough to run this algorithm, and then it's able to factor those pre-shared keys. Let's also see what we're not talking about. We're not using quantum computers. So we're using some of the quantum properties, but quantum key distribution doesn't require any quantum computers. So everything we're talking about in this presentation can be done at room temperature, right? For a quantum computer, you need specialized rooms with extreme cooling, etc. But in this case, it's equipment that can be used, as I said, at room temperature. We're also not securing the network with quantums, right? The way we transmit data from one side to the other, from Alice to Bob, is still using classical MACsec or IPsec. It's just the way we are distributing keys between both parties that are using properties of quantum to do so. So let's see what it does and how it works. So some of the language and terminology. The biggest difference probably between, as the physicists call, classical networking, what we're doing today, and quantum networking is that in classical networking, a classical bit is always a 0 or a 1, whereas in quantum, a qubit can be 0, 1, or anything in between. And you only know if it's a 0 or 1 once you observe it or measure it, as they say. And that phenomenon is called a superposition. And one of the most interesting properties of a qubit, especially in the context of security, is that you cannot copy it. That is also the biggest downside of a qubit, as you cannot transport qubits over CWDM or DWDM equipment, especially if it's amplified, because then the quantum state, the qubit, gets lost. So it is an advantage, and that is where QKD is based on. But again, it's also something the physicists will need to solve going forward in order to make this better scalable. As I mentioned, the qubit can be 0 or 1, and that is called a superposition. And in very simple words, by the way, I'm not a physicist, and this is by far not a physics class. But in really basic terms, a superposition of, in this case, a photon is basically a laser that puts the photon into a certain polarization. And once it's polarized or in superposition, you send it to the other side. And the other side can measure that photon and read or measure the superposition. As I mentioned, you cannot copy that. The state you bring it in, so the superposition, is really, let's say, sensitive, right? So you need high quality fiber. You cannot amplify it. The distance is limited. If you use it in a passive CWDM or DWDM system, it could work, but you need to be aware of interference of other sources of light as well. So there's still lots of work to do there. By the way, on many of the slides, you will see links. So if you're interested in reading further, I would suggest to visit the links. Quantum teleportation. Probably you've seen it in movies, that we cannot teleport physical objects. The only thing we can teleport is a state or a superposition, basically a photon that is brought into or has a certain polarization, and that polarization describes the quantum state. So that is the only thing, unfortunately, we can transfer. There are several ways to do that. In QKD, we basically have one side that is always sending the photons to the other side. So Alice will always be the one polarizing photons and send those to Bob. Bob has a special filter where it puts the photons through, and so it can measure the superposition of the photon, and that is then called teleportation. So you teleport a state from one side to the other. There's also entanglement, which basically means you bring a polarized photon really close to another photon, and that photon then will take over the superposition state of the first photon. And then if you bring them apart, they will still have the same state. So if you measure one side, the other side will collapse into the same state. Again, really short description of how this works. Please visit the links if you want to read further. So as I mentioned, some of the advantages, obviously the biggest advantage of using quantum to distribute, in this case, key material, is that you cannot copy the photons. So you are guaranteed, as far as you can guarantee, obviously, you're guaranteed that the only one who will know the state of the photon is the intended receiver. The superposition also collapses if there's an eavesdropper, and that is why it's called it's called that you cannot clone it. So if Eve interferes in the conversation and tries to eavesdrop and measure the photon, the superposition collapses. So if then Bob will measure the same photon, it won't be in a superposition. So Bob will know that someone else already measured the photon. And probably the most interesting thing is that it's using physics over math. As I mentioned, at one point, a quantum computer will become so powerful that it can easily factor prime numbers as we currently use it, but you can obviously not factor physics. You cannot factor the state of a photon. So that makes it much more secure. As I mentioned, there's also a couple of challenges. For example, decoherence. And decoherence describes the ability for a photon to maintain superposition over time. So that is also an issue the physicists will need to solve going forward. You cannot really store qubits for a longer time. So this is only really usable currently for real-time applications. Another challenge is the fidelity. Fidelity describes basically the quality of the qubit. As I mentioned, there are challenges when using quantum key distribution in setups or networks where you use DWDM or CWDM equipment. And so the quality drops dramatically if you have other light sources, for example, on the same fiber as well. And scaling is an issue, scaling in distance. As I mentioned, you cannot amplify the signal. So currently, our current commercial available QKD solutions are only usable up to a distance of around 120, 140 kilometers, depending on the quality of the fiber. But also, as you might have figured by now, it's always a point-to-point system. So how do you scale this, for example, in a multi-point VPN setup? So a term you might have heard by now or might have seen around is quantum internet, or is it quantum networking? So let's see about that. As I just mentioned already, basically there is no quantum internet currently, right? A quantum network at max, but that's basically a point-to-point connection using a dark fiber. So it's in this case still two end nodes using an optical connection or free space, could be as well using a satellite. But that is the state where we are. So we are still far away from a quantum internet. In order to reach the state where we could talk about the quantum internet, we need repeaters, for example, or we need to be able to amplify the signal. So there's still quite a lot of challenges. One of the things the physicists are currently working on is what is called an entanglement swap. Basically, to simply describe that, is Alice and Bob entangle two photons. As I just mentioned, if you bring those photons really close together and you take them apart, they will have the same quantum state. Now, if Bob and Charlie do the same, and then Bob does a so-called entanglement swap action, then Alice and Charlie have entangled photons. So that is a potential way to overcome the distance limitation. But this only currently works in in the labs of universities and some commercial parties as well. So we are still quite far from a quantum internet. There's work going on in IETF, in ETSI, ITU, and other standards organizations. And as you can see, there's also already sort of an OSI model, but lots of it is still theory. And so there's still lots of work to do before we'll see a quantum internet. And if at one point we'll see a quantum internet, will probably look like, looks like a little bit as you can see on the drawing, where a end node will have two connections that could be over shared fiber if we're at the point where we can actually use CWDM or DWDM. But there will probably always, or at least in the near future, you'll always have a classical link and a quantum link. As I mentioned, we're currently in QKD only teleporting or transporting quantum states. And if you compare that to the evolution of the internet, this is at a point where once the internet started, we could send, or we tried to send login to the other side. We were able to send the L, the O, and when they sent the G, the whole system crashed. So this is still much slower than your old dial-up modem, for example. So for the short term, a classical link will still carry the data, and quantum will only be used for synchronization, for key distribution, etc. Obviously, there will be a point where routers will also be able to, next to classical data, also route quantum or have a quantum data plane. But currently, that is not possible yet. So some possible applications for quantum in networking. Some of them I've mentioned already. A really good use case would be clock synchronization, for example. Secure access to resources using based on key distribution, for example. Obviously, also communication between quantum computers to either transmit data or share a memory, for example. But the most used and actually most or available solution currently is quantum key distribution. There's a couple of vendors who have commercial solutions. You can actually buy already and integrate in your networks. So let's see how quantum key distribution works. How we use it in symmetric key cryptography, how QKD works, and how we can make it applicable in security mechanisms as we currently know it. The biggest issue, as I already mentioned, with public key cryptography is how Alice and Bob are going to agree and share their pre-shared key. As I mentioned, the encryption and decryption of the data itself is already quantum resistant because it's using AES 256 and you can scale that up easily. But the sharing of the key itself is the biggest issue in public key cryptography. In symmetric key cryptography, you are end-to-end secure if Alice and Bob have a way to communicate the key between each other in a safe way. And that is where the weakest link of symmetric key cryptography is. So, as I mentioned, current mechanisms to share that key, RSA, Diffie-Hellman, etc., are based on mathematics. So at one point, as it is currently expected, a quantum computer is powerful enough to factor that key, and so our eavesdropper is able to eavesdrop on the communication. On the other hand, the symmetric cryptography mechanisms and AES which is being used in MACsec and IPsec, is quantum safe. So now if we combine quantum physics, so combining physics with AES, we have in theory, secure way of communicating. So let's use MACsec or IPsec and use QKD to distribute the keys. And in order to do so, Bennett and Brassard came up with a protocol or a mechanism to distribute those keys, leveraging the properties of quantum. And they came up with it in 1984. Hence the protocol is called BB84. And how it works is on one side you have Alice and on the other side you have Bob. And they are using these polarized photons to communicate with each other. Then if you look at how it works, Alice polarizes photons, and as you can see, she does that in sort of a random way. The photons she's sending have a polarization of 0 degrees, 45 degrees, 135 degrees, then 45 degrees again, etc. She does that over a dark fiber, in this case, quantum channel. Bob has a so-called photon detector and reads the state of the polarized photons. And then the next step is that Bob applies a random filter sequence to measure the photons. Because he doesn't know if Alice has sent polarized photons in, or in which polarizations he sent the photons, he's applying random filters to the photons he receives. And as you can see, the first filter will pass 0 and 45 degree polarization. The second filter will allow 45 and 135 degree polarization, etc. So they measure these photons Bob receives from Alice, and he stores the result. Then the next step is Alice and Bob exchange the filters they've used. And now, as you can see, in some cases, there is a match if they've used the same filter and the photon has passed the filter. So, for example, in the first photon that has a 0 degree polarization, they both used the filter that allows or passes 0 degree or 90 degree polarization. So there's a match. They use a public data channel to to share those filters. And basically, if someone would eavesdrop on that conversation, you only have the filters, but you don't know which photons have been sent. The other way around, if you eavesdrop on the quantum channel and you don't know the filters that have been applied, it's useless that you might have measured some of the photons. And the reason why this is so secure is because if there would be an eavesdropper on the quantum channel, reading the photon states, as I mentioned, the quantum state collapses. So Bob won't have any photons to measure, or at least he receives photons with a false quantum state. And as the filter is only applied after Bob receives the photons and he applies random filters, a potential eavesdropper doesn't know which filters Bob have used. So that is why this is inherently secure. Now the next step is for Alice and Bob to sift through the results. And as you can see, a key starts to appear on the photons where they have applied the same filter and that have passed the filter. So in this case, the key both Alice and Bob can use is 0101. Again, this is a really short explanation, and there's a really good video on YouTube that describes this as well, which is definitely worth watching. So the next step, obviously, is that there's two devices on Alice's side and Bob's side that actually have generated a key. The next step then is for our routers or firewalls or servers to actually start using that key. And that is described in what is referred to as the ETSI protocol. ETSI came up with, or the ETSI API, I should say. ETSI came up with a standard for an API that can be used by QKD vendors and router vendors to exchange that key material and fetch the keys from the QKD devices and use that in security mechanisms. So if we walk through how that works, we have Alice on the left side, Bob on the right side, and they want to use quantum key distribution to exchange a key and use that in a security mechanism. So both Alice and Bob have a QKD device. As I mentioned, Alice will generate and send polarized photons over a quantum channel to Bob. Bob has a photon detector and can read the states of these photons. Both will also have a router that has a connection between them, have a connection that could either be MACsec or IPsec or any other security protocol. That obviously would allow for hitless key rollover, as that is one of the interesting things, that this QKD setup can generate keys at a certain rate, could be a couple per second or even more. And so if you roll over the key obviously fast enough for the security protocol you're using, it's much harder to intercept that communication. Alice and Bob also have between their QKD devices a quantum channel that's used to send the polarized photons, and they have a data communication channel that is used to exchange the filters applied to the polarized photons. Now, if Alice and Bob's routers want to start using these quantum keys in MACsec, they start with doing a key request to the QKD device. And the way that works is, as I mentioned, the ETSI API. So they send a call to Alice QKD device for key request. Alice receives a key material and a key ID. She sends that key ID to the router on Bob's side. Bob can use the key ID to request that key from the QKD device. Obviously, he then receives hopefully the same key. Now both start using that key for their MACsec connection, and their traffic is secured using QKD. There are some implementations of this already. There are some router vendors who have built scripts and etc. to use this. As far as I know, there is no production code yet on a router vendor side, but there's quite a few vendors of routing equipment, but also optical equipment that are testing with this and integrating this. Now I'll hand it over to Ashwin, who will walk you through how this could work, how some of the configuration looks like, and how this looks on CLI to configure it.
This is a demo on a quantum safe IP6 solution, which is implemented as part of a proof of concept. So this is the setup topology. Here we use two SRX 5K devices at both Alice and Bob's side. We have a QKD out-of-band network. So there is a quantum key transmitter, quantum key receiver, and there would be a channel with which it generates a shared secret. So at Alice side, we request for a key with the help of an HTTPS request. And we then receive a key and key ID from the QKD device or quantum key distribution device. Alice keeps the key and shares only the key ID towards Bob with the help of some modifications in the existing IKE v2 protocol. So as part of the IKE negotiation, we also share the key ID information towards Bob. So once Bob receives the key ID, he can use the key ID to fetch the corresponding key from the QKD device. So key ID is something which is uniquely identifying each key, since the QKD out-of-band network can generate multiple keys. So now we have a symmetric key at both Alice and Bob's side, and this key can be mixed with the existing IPsec SC key materials that is generated as part of IQ2 protocol. And we have a final key material which is meant to be quantum secure, and it is this new IPsec key material that is used to establish IPsec tunnels, so that the tunnel is meant to be quantum secure. So as part of this demo, we would be establishing IPsec, a quantum safe IPsec tunnel, and we would pump bidirectional traffic with the help of Ixia traffic generator. So it has two endpoints. So from the first endpoint of Ixia, we send traffic towards SAA, which is then encrypted, and send the traffic towards Bob via the tunnel. And once it is received at Bob's side, it would be decrypted and sends back towards the other endpoint of Ixia. So we have another traffic item which sends the traffic in the other direction in the similar fashion. So we also ensure that the traffic is not impacted upon expiry of the essays. So upon lifetime expiry, we would request for new keys from the QKD device, and it then offload the traffic from all the tunnels towards the new tunnel. So here there are two windows open. The left side black window is for Alice and right side blue window is for Bob. So we have IC and IPsec specific configurations already done, and there is an additional knob added to configure QKD specific information. So as part of the QKD profile, we specify the peer SAID, local SAID, and the URI of the corresponding QKD device. So it is this profile that is then mentioned in the gateway configuration, which is the IC gateway configuration. So once we have such a profile mentioned as part of the gateway configuration, this gateway is considered to be quantum enabled. Similarly, this configuration, a QKD specific configuration is done at Bob's side, where we have the QKD specific profile, and the profile name is then mentioned as part of the gateway configuration. So we already have the IC and IPsec essays established. So in order to get a new IC and IPsec essays, and in order to get a new key from the QKD device, we can clear the existing essay. It takes some time to come up. Yeah. Now you can see the index has been incremented from 110 to 111 for IKSA, and also it has been incremented for IPsec essays. So we can now check the key ID and key that is received from the QKD device. For that, I will search with a quantum keyword. So here you can see an HTTPS request that is sent from the daemon in our Juniper router towards the QKD device in a format as per ETSI specification. So in this HTTPS request, we specify the QKD server IP address, peer SAID, and it is with encryption keys at the initiator side. And we can also specify the size of the key that is needed and the number of keys. And this is the response from the QKD device, and the response contains key ID and key. So we already have the initial IPsec key material that is generated with IQ2 protocol. So this key material is then mixed with the key from the QKD device with the help of a pseudo-random function to generate a final IPsec key material. So it is this IPsec key material that is considered to be quantum secure, which is then used to set up IPsec tunnels. So if we search for the same key ID at Bob's side, we should see the same key. So I will then enlarge Bob's window. So this is an HTTPS request from the daemon running at Bob's side towards the QKD device. So it contains a key ID. So this is a key ID that was communicated from Alice towards Bob via the IKE v2 protocol. And we specify the QKD server IP address and the peer SAE ID. We then receive the corresponding key ID and key from the QKD device. So it is this key which is symmetric at both the ends. And so we have the initial key material that is then mixed with the key from the QKD device to generate a final IPsec key material. So it is this new or final key material that is used to establish tunnels. So now we already have the tunnels established. We can now pump traffic. So I use Ixia to generate traffic. Now you can see the traffic is going through with a negligible drop, which you can ignore. It happens due to since we have enabled some logs. So in order to check if the traffic is going through the tunnels, we can use show security IPsec statistics output. You can see the encrypted and decrypted packets are getting incremented. So we have a lifetime specified for IKE and IPsec essays. So whenever the IKE lifetime gets expired, it tries to do renegotiation and it tries to fetch a new key from the QKD device, and then it establishes a tunnel which is a backup tunnel, and we then offload the traffic from old tunnel towards a new tunnel. So you can see we initially had an IKSA having index 113, and this was the timer expiry. So this is a hard lifetime. There is an internal lifetime called soft lifetime. So upon soft lifetime expiry, it would try to create a backup tunnel and offload traffic from old tunnel towards a new tunnel. So now there is already the expiry happened, and it generated a new essay with a new index. So whenever the IKSA gets expired, even the IPsec essays would be renegotiated. So here we have specified the lifetime as 180 seconds, which is 3 minutes, which is the minimum possible lifetime. And also the reauth frequency is set to 1, so that every time the IKSA expires, it does a reauthentication, so that it tries to fetch a new key from the QKD device. So now you can see the traffic is not impacted even after the lifetime gets expired from the essays. So that's all. Thank you.
All right, thank you, Ashwin. As I mentioned, this is not production code yet, but we developed this in order to learn for ourselves how it works and see how we can use those QKD keys in this case in IPsec. Other vendors have similar implementations as well. So it's definitely worth checking that out if you're interested. As I mentioned, applicability, QKD is available from Toshiba, from ID Quantique. There's a couple of vendors who actually sell these QKD boxes. Most of them expose the keys using this Etsy REST API. I've put the link up here to the specification. There's also a few simulators available that either developed by the QKD vendors or even freely available for you to test, that expose the REST API so you can fetch the keys and get the key IDs, etc. Then come up with ideas. How can we use QKD? Which security protocols? I already mentioned MACsec, IPsec. But it could also, for example, be used in TCP/AO, which allows for dynamic key rollover as well. But there's also a couple of challenges still and things to solve, right? Probably the biggest challenge is how to overcome the 120-kilometer distance. Do we need quantum repeaters? Can we use some SD-WAN kind of solutions? Is it satellites? I know in China they're testing with satellites. Obviously, you can span much larger distances than the 120 kilometers over fiber. But the downside, obviously, is that you need to put a dish on your office or a data center rooftop. How can we leverage and use keys where there's no QKD devices present, right? Can we, for example, for remote or home workers or maybe even mobile users? And what about multi-point QKD? As I mentioned, all the QKD systems are basically point-to-point. So can we do something with entangling more than 2 photons and or come up with something smart? So there's still quite a few challenges, but for some applications this is as I mentioned available. So yeah, feel free to reach out. There's here also some further reading. As I mentioned, there's work in several of the standards organizations. There's the Quantum Internet Research Group in IETF that is quite active, and some of the things are discussed here. Etsy is working on standardizing the protocol to fetch those keys from the QKD devices. ITU is working on it. There's lots of material from universities. I'm based in the Netherlands, so the university in Delft, for example, is working on it, but also universities in US and UK and in other countries. Other questions? I can take questions now, or feel free to reach out by email afterwards. Thank you very much.
Do we have any questions for him?
So there's been this like boogeyman of quantum computers forever. Like it keeps coming up as this thing. Is there like a timeline as to when you see it actually being a thing? In years, or you said soon, so I was wondering if you could quantify that a little bit.
Yeah, excellent question. So as I mentioned at the beginning of the presentation, what we just discussed isn't about quantum computers at all, but obviously we're trying to protect against quantum computers. To be honest, I've visited the labs at universities, and I've spoken with quite a few folks in research. Quantum computers that are usable will be here earliest in 10, 15 years probably. It's absolutely a fair question. It is also a fair question then if we would need QKD or post-quantum cryptography at all before that time. I think it would be good to start looking into it as we're doing, and as we showed that at least you are aware of what the threats are and some of the options to protect your network. But yeah, quantum computers are still quite far out. That's absolutely a fair question.
All right, thank you so much, Melchior. That's all the time that we have for questions.
All right, thanks for having me.